Okay, so today's lecture, our flip lecture, we're going to talk about, the problems with concurrency and race conditions. And at the heart of it, all of these fall under this category of, resource allocation problems. And so what's the resource that we are dealing with over here? So who can answer that question? We have tasks running on a computer, and what's the resource that we are dealing, what's scarce, what is being shared?
Is it when multiple processes are trying to access the same file or value, they can access them at different times?
Could you speak a little closer to the mic, please?
Is it for a race condition when different processes are trying to access different files or values, and they could change the values at the same time?
Yeah, so the resource here could be like some kind of a memory structure, right? So memory could be a resource over here in our operating systems lectures. The resource there was the CPU, right? All the tasks want to share the CPU. How can you share this really well? And and this is basically like a fact of life, right? There's always, like in economics, there's a scarcity theory that resources are scarce. How do we divide them among many people or many parties that need them? And there are some very these so this lecture is probably full of like all the little tricks and all the little sort of puzzles that are there when we have access to resources that we are trying to share. We're trying to share memory in this case, and but we are trying to share it over time, right? So that's what makes it tricky. And so concurrency just means that, okay, well, we are concurrently at the same time, simultaneously trying to access the same resource. And how do we resolve conflicts in that? So I have two kids at home, right? I mean, one is 3 and the other is 6, and they have tons and tons of toys, but at any time they always want the same toy, right? So then I have this resource allocation problem with them, or they have this resource allocation problem that they make up, that no matter what other toys are there, they always want the same toy. And then we need to figure out how to deconflict them. And so one simple way to deconflict them is I tell my older daughter that, look, tell your brother that he can she have the toy for 2 minutes or 5 minutes, and he decides whether she has the toy for 2 minutes or 5 minutes. And then he hands it over to her for a short lease time. And then when he wants it, and he asks her, can I have it for 2 minutes or 5 minutes? And then she decides, can he have it for 2 minutes or for 5 minutes? But she has to hand it back to him when her timeout happens, right? I mean, her timeout of the toy, not her timeout. So this way they basically are deciding between themselves, okay, you can go next, but then you need to give me access after 2 minutes or 5 minutes. And this is one way to deconflict it. In real life, it works maybe like 20% of the time, right? So but that's real life with kids. Now we are in much simpler world over here with running concurrent threads over here, right? So what are threads? So we have processes, and processes are things that we spoke about in the previous lectures, were like tasks, right? So tasks are an embodiment of a bunch of functions that we are running. So say like this whole PowerPoint is one like a collection of processes, but it is a task over there, right? So and similarly, the Zoom thing over here, the Zoom application is a task, and it has a bunch of processes in it. And so we are going to use tasks and processes interchangeably, right? And then now, what are threads? Threads are, you can think of them as like multiple threads can run within a process. But for the matter of this lecture and for this class, we can treat all of them to be quite the same. Tasks, processes, and threads. Technically, they are quite different, but that's when you go into Google or Amazon, and then they say, no, 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 that's a task. A task can have multiple processes. A process can have multiple threads. But in this lecture, we're just going to treat them all as look, there are different, executable, elements or executable embodiments of that can access the processor, that can access resources, and they can run independent of anything else, and they want to access these resources. And so these are, they can run asynchronously. So far we've looked at, tasks that are either, periodical, as that's what we are looked at for our two scheduling algorithms, or they could be tasks that can run like the interrupt task, asynchronously or sporadically, like that, right? So they're independent, they have no reliance on each other, and they could have some synchrony between that the frequency at which they run, and they all want to run at the same time, right? So that's the problem over here. So let's go to the first question on what. So did you guys understand this race condition, like what this race condition is and how you get like different possible outcomes from this? Let me see. Or
I kind of got it, but I didn't understand where you wrote the slide right after, where you compiled just the simple x is equal to x plus 1. Can you explain why there's a race condition there?
Yeah.
Like, because it's trying to access the value after it might have been changed or something?
So think about like, x equals x plus 1. That's some code written in C, okay? And so when you compile this code, say this code compiles into 3 different assembly, lines of code, like that, right? So now, so even though it looks like it's 1 line of code in C, it actually gets compiled to 3 assembly lines of code. So now you can just think about it like this, that this is one task that is executing these 3 assembly lines of code. And then you can have another task that can just interrupt this task at any time. And where can it interrupt this task? It can interrupt this task after the first assembly line of code, after the second assembly line of code. And so this task can be interrupted at any point. So these are the gaps, right? So once the processor has finished executing the current task, then the processor can like get interrupted by another task or by the kernel or by an interrupt. So this is just saying that, look, while you are executing this, so say I'm writing this x equals x plus 1, and so far I have copied over x, and then now I get interrupted and I get preempted by another task. That task basically goes and writes x equals, say initially x equals x plus 1000, and then it returns, and then we come back to this task, and then it adds 1000, it adds plus 1 to that, and then it basically writes that value back to x. So if I get interrupted in the first arrow space over here, I could basically go and make x some other value, and then I add 1 to it, and then if I store that value, I basically get like x equals 1000 plus 1 instead of just 1, because this x is like a globally shared variable. And if I get interrupted and someone else writes the value to x, then it's free for all, right? Or say I loaded x over here, and then I added 1 to it, and then I'm going to save that value of x plus 1 back to x, but then I get interrupted, and I go and say x equals x minus 10,000, and then I write that value back here, and I don't get this value that I'm expecting here. I don't get x plus 1. So if I'm just counting up plus 1, plus 2, plus 3, sometimes I would get minus 9,999 because I got interrupted by another task. So this other task is some phantom task, right? We don't show that over here, but that's basically just saying that these are where the code is sort of porous, right? And this is the kind of gap where we can actually have another task come in. And if this is a global variable, then we can actually change that variable. And that's not really the intended sort of, computation that these 3 lines of code were trying to do. But these 3 lines of code did not actually run sequentially. They were intended to run sequentially, but you could have other sort of tasks come in and preempt this task. And so if you go back to like our lecture from last week, we were showing like, say task 3 was, for example, in most examples, always getting preempted by task 1 and 2. So say this is task 3. Task 3 just ran the first line of code and then the second line of code, and then it got preempted by task 1. Task 1 went and changed x to be minus 2000. And then we come back over here and then we say, okay, let's write x back to x over here. So, or this x plus 1 back to x. And then we overwrite that minus 2000 to this. So both these tasks are fighting over the same shared value. And so which one wins out basically means that there is some sort of corruption in the calculation, because this task is not running, you know, sequentially and without any sort of, you know, without any changes, right? In this point over here. Yeah, the task could get interrupted. Another task could run something else and come back and not touch X, which is also fine, because then effectively this runs sequentially and the correctness of these 3 lines of code does not change, right? So our whole point over here is that, well, if I have, even though I put this as a single line of C code, in assembly, it is actually, and in machine code, it is actually it has preemptible points over here. So it's not that this code runs. What is the key word? That this code, we want it to run without getting interrupted by any other task, that it runs, you know, fully, right? So what is the key word for that?
Maybe something like atomic operations.
Yeah. So we want this, if we want this to run atomically, then we have to do something else, right? And so what could we do to run this atomically?
You could like lock it.
We could lock it. So that's one way. What else could we do?
Just make it a single instruction.
Make it a single instruction. That's another good way. What else could we do? You can play God with the system, right? You can basically say, hey, I'm going to disable all interrupts, right? If I don't get interrupted, then I'm not going to come here. I can disable preemption. I can make it non-preemptible, because I can just say, look, we don't want anyone to mess with our code. And so there are many different ways, right? So and so we will, that's what the rest of this lecture is about, is looking at these different ways. So this example over here, so maybe just give me a show of hands. Let me see if I can see everybody on this, right? So, okay, there are just 8 people here. So, so how many of y'all actually went through the slides here before? Okay, so how many, so if you did go through the slides or didn't go to the slides, no one's judging here, but I just want to get an idea of, you know, did you understand this example over here? Kind of, sort of. Okay, good. You want me to explain it? I can explain anything. Okay, so just ask for it. Okay, you can be super lazy and just say, yeah, explain everything, and we can do that. That's also fine, right? I'm here for you guys over here. Okay, so let's go to the first question. So the second question was, what is this kernel stuff over here, right? So so the critical sections and the kernel, right? So a critical section is basically just what we looked at over here. That, like, suppose we are looking at this bank transfer example, right? A critical section is when we are manipulating, you know, any shared memory location or any shared variable or any shared value that is accessible to multiple processes, right? So we have a withdrawal process and we have a deposit process, right? And here the question was, look, I'm going to, I want to basically, I'm withdrawing $500 from my account. And at the same time, while I'm withdrawing that money from my account, Fen is depositing 5,000 into my account, right? I mean, it's a rare case Fen deposits anything in anyone's account, but in this case, we got lucky, right? So now So while I'm withdrawing this, so I read the account balance and it says 500, and then it subtracts 500, and then it's before it, and it's starting to give me my money, and then it basically writes back the value of my account balance. Say I had $1,000 in my account, then it writes back 500 into the account, right? And so if I don't protect these lines of code and the deposit comes in at the same time, the deposit could interrupt me before. It could come in first, and then I could come in after that. Or I could read my account balance, and then the deposit could come in, read the account balance, same account balance, add 5,000, write the account balance. So in the first case, I have only 1,000 in the beginning, and then it basically goes and adds 5,000 to that account and writes the new account balance as 6,000. So then in this case, then I come back to the withdrawal process over here. I subtract 500. So in this case, I locally have only read the account balance to be 1,000, but the account balance actually just got updated after I read the account balance here to 6,000. So then when I subtract 500 and then I write back 1,000 minus 500 and I write back 500. So this account balance is a local variable because I'm just reading that locally. And so even though 5,000 was added to it, I basically just write back 500 and I basically lost $5,000, and whatever pen deposited, I did not get it because this deposit task came in the way, right? And another way could be that I read the account balance, I subtract 500, and then I get interrupted. And then I basically go and read this account balance, add 500, and then I write back this account balance of 500, and then it adds, and then it does this add 500. Then I come back to this, and then it adds 5,000, and I get 5,500. Then that's the normal process, right? So, and then who can explain to me what happens where we get a third case, right? Where we have in the previous example, where we have this case 3, where the balance could be 6,000. Who can explain to me how the balance can be 6,000?
You deposit it, so then it's 1,000, and then
no, I deposit. I'm depositing 5,000 into the account, right?
oh,
So how can I get 6,000? You could just read that slide and tell it back to me. What?
should I just read it? Is that wait?
No, you could just explain it right back.
So on the slide, it just says the deposit thread runs first, and the account balance. So it reads 1,000 and then adds 5,000. So you have 6,000, and then it's preempted, and the withdraw thread is scheduled to run. So it reads the balance as 1,000, and then subtracts 500, and then stores the result 500. So then it ends up with just 6,000.
Yeah, but the sequence in which you said it is not exactly the sequence, right? So we don't start we start with which thread. So we are basically you're close, right? So we read this account balance. It's 1,000. Then we basically go and get interrupted and go and finish the full withdrawal process, and it writes a balance of 500. And then we basically, but then we come back to the deposit task, and we had 1,000 to begin with. We add 5,000 to it, and we write account balance of 6,000. So it basically overwrote the 500 in the process over there, right? So then we got 6,000, and so that's great, right? I wish that happened more often, right? So so even though I withdrew 500, I actually still I got 500 in free money then, right? So So the point here is that, now what you want to do, you want to basically make this code over here and say, look, this code, if once I start running the read, subtract, write, nobody should come in the way, and I need to acquire a lock and do that, right? So I have a question. How many of y'all have taken SYS 240? Did y'all cover locks and synchronization in that? Okay, how many of y'all have taken, any of y'all have taken operating systems? Okay, so you'll cover this again in that. But it's good you take it here. So this is a critical section. A critical section is saying that it's a section of code that we want to protect so that it runs sequentially and is not open to any sort of interruptions or preemptions. And so that's what we want to protect, right? So, and then, so then what are these preemptive kernels? Preemptive kernel, what is a kernel? Who can answer that question? So it's like asking what's an operating system, right? So a kernel is basically the task 0, or basically the parent task of all tasks that are there. And the kernel is essentially what is running, and the scheduler, what is running all the operating system processes, right? Suppose the operating system has to, you say, can I open this file? Then the file open message goes to the kernel. The kernel says, okay, you can open this file because nobody else is writing to it. Or if you want to write to the file, it says, no, you can't open this file because someone else is writing to the same file. And so all the requests that you make in the operating system, they all go to the kernel. And by preemptive kernel, non-preemptive kernel, we just mean that the scheduler inside this mother task, that is, the task, the operating system's parent task, is using a preemptive scheduling algorithm or a non-preemptive scheduling algorithm. So that's what we mean by kernel, right? So the next question was then on, was on what are semaphores, and then what makes semaphores special, right? So let's look at that, and then we can come back. So let's look at semaphores over here, and so semaphores is an operating system, is a special command, right? Is a special instruction that is written in a C library, but that is supported by the operating system, right? So, and let's look at what that means, right? So the operating system basically says that whenever you use a semaphore, then it'll always go and check what is the value of the semaphore before it actually executes that, right? So, so in this case, what we're going to see is, suppose I have, this is the implementation of a semaphore, but let's first look at how we would use it. Then we'll look at what the semaphore means. I would initialize first this as a mutex. A mutex is just a name that we give for a semaphore. And we say, like, okay, look, to protect this critical section, we need to basically protect it with a mutex. And we can have different mutexes for different types of protection. And that's what we'll look at as we go through the later examples. And so before I enter the critical section, I first initialize a mutex to be just 1. Okay, because I'm basically saying that 1 means that at most one task can execute a critical section at any time. So then I say down, and the mutex's address over here. And I'm just basically reducing the value 1 to 0. And then I execute the critical section, and then I basically add that back. When it becomes 0, it just says that there are no more tokens. If you are another task and you want to execute a critical section, it says, sorry, there are no more tokens for you to execute your critical section. What you need to do is wait. And and that's when you call the operating system and say, hey, I'm waiting for this mutex token, and there are no tokens there. So then the operating system says, you know what? I'm going to put you in the waiting queue, and I'm going to basically put you to sleep. to put a task to sleep just means that it's just going to be put in the waiting queue or the blocked queue. And whenever the mutex is available, the operating system will go in and search for a task has been waiting the longest for that mutex, and it'll go and wake it up. By waking it up, it just means it's going to take that task in the linked list of these different queues that are there for the operating system and move it from the waiting queue to the ready queue. And then the task is basically in the ready queue, and it's ready to, whenever it's ready to get executed, it becomes a running task. And then it can then capture that mutex and then run its own critical section. So essentially this mutex over here is the way it's implemented over here as a semaphore, and a semaphore is a special library that is supported by the operating system, so that whenever we check, is the value greater than 0? If it is greater than 0 and we call down semaphore, then it reduces that by 1 and basically says 1 token has gone for this critical section. Or if the value is not greater than 0, that means there are no more tokens left. It basically says, take this task or this event that had called this mutex and put it to sleep, basically put it in the waiting queue. And once you're done with the—
Sorry, I have a quick question.
Yeah.
Oh, my sound just went. I can't hear you. 1 second. Okay, I think I can hear you now again. Sorry, my sound just went. I was wondering, why would it make sense to have more than 1 token? Wouldn't we just end up with the same concurrency issue again?
So let's say you want to say, so if you and me both want to write to the same file, right?
Mm-hmm.
And then we would basically want to say, look, I'm editing this file now. You come back later on and then you can edit it. Let me make my updates. And so in that case, you just enforce this semaphore and said, only one of us can write to this file. Mm-hmm. But then if both of us want to read the same file, then we'll say, hey, that's fine. You can read the file and I can read the file. And then we can have more than one of us reading the file, right? So then I don't have a limit on how many people can read it. But, mm-hmm. but if someone is writing to it, then we want to have a limit on that. So, okay. So it depends. What are you doing with the critical section, right? Are you just reading the critical section? Are you writing to it? Let me give you another example. Suppose we want to say that it's a. We'll come to some examples in the latter part where we want to have, say, more than one party run in the critical section. Then we can allow that. But yeah, your observation is right that whenever we want to, the very common semaphore is just a binary semaphore, which just says that at most one party can go and edit that section or can go and write to that section there. So that's the most common semaphore, but you'll see in examples that we have at the latter part of the lecture, you have multiple, you can have more than one come in at that point in time.
Great, thanks.
Yeah. Okay, since we can use this token method in internet flow control, I don't understand that question. Since we can use this token method in internet flow control. Zia, you want to explain that a little bit better? Oh, can we use this like a
hello?
Yeah, go ahead.
Oh, nice. So seems like you can use this like token, because I've been seeing other different classes that you can use like this, like assigning tokens and like decreasing tokens and increasing tokens stuff to do like a flow control or something. I was just wondering if you can also use the same method in, like, say you have different threads and you want at most like 10 threads to be running at the same time and just like sleep all the other threads if they're like, I don't know if that's possible or if it's useful. I'm just wondering if it's like.
No, that's actually a great example. I should have mentioned that. Yeah. So that's going back to the earlier question of, yeah, he's back now. So the question was, this is another good example of, why would we want to have, not a binary semaphore, but a semaphore that could be more than one, right? And so Ziao's answer is, suggestion is that, yeah, look, what if I'm running, I want to run like, 10,000 threads on my AWS instance, but I didn't cough up enough for more than a small instance. And if I run 10,000 threads on that instance, it's just going to choke. And so what I want to do is I want to sort of get a medium AWS instance, and I want to dedicate, like, to say, I want 10 threads to run on each of the 8 cores that I have in this medium instance. And I don't want more than 10 threads to run per core, because that's going to choke up that. So I can basically have a semaphore to say, okay, I can count to having 10 threads running on the same core. And then once the 11th thread comes in, it says, wait, you got to wait till one of these 10 threads finish up, like that, right? So, or you can think of it like, if you download like a lot of torrents at the same time, like that, right? So they all are fighting for the bandwidth, and you're like, hey, I just want to watch like this show, right? And but you're also downloading many other files at the same time, and so they're all sharing the bandwidth. And now you want to say, hey, let me reduce, instead of downloading like 8 different files at the same time, I'm just going to allow 2 files to download at the same time, and that'll speed up the throughput allocated to the first 2 flows. And then you can get to starting to use the first 2 files as an example there, right? So yeah, so that's another way. It's basically doing like it's doing a resource allocation by throttling, like how much of the resources are available to everyone versus how much of the resources you want to focus. So resources are not just, either you use it or you don't use it. You can think of resource as going from, I can use 10% of the resource to I can use 100% of the resource. So, but for the sake of, understanding mutexes, it's most intuitive to understand a binary mutex where you either get to use the critical section or you don't over here, right? And so here the question is also that we have this critical section, and it can be used by multiple threads, right? So in your sort of world of like of what we've just covered in the last week of tasks, essentially you can think of this as a function, and this function is being called either by task 1 or by task 2. But task 1 and task 2 can't call this function, at the same time, or they can't be calling this function and getting interrupted, and then task 2 calls the function again at the same, after interrupting task 1. So basically it just says that, look, if task 1 is running the code and it gets interrupted during this critical section, and then task 2 comes in and says, hey, I want to run this critical section now because I preempted task 1, then it says, sorry, you can't, and we're going to put you in the waiting queue. And then task 2 basically gets relegated into the waiting queue. And then task 1 gets back the access over here, finishes up. And once the mutex is released, then we come to this up semaphore over here where it says, hey, is someone waiting in the waiting queue? Yeah, task 2 is waiting in the waiting queue. Let's go wake up task 2. And then it basically adds it basically goes and wakes up task 2 at this point. Otherwise, if no one's waiting, then it just releases the token and it adds a 1 back to this binary semaphore. And then whoever comes in later on is free to use it. The point is that once any task is done with the critical section, then anyone else can get it. It's not like it's blocking it forever. What happens if a task comes into a critical section and actually inside the critical section, we have a sleep? So what would happen then? Then nobody can run, right, after that point. Basically, it's just saying that, like, look, we have a big, let's say you're taking some history course, and there's only like 1 book available in the library now for that history course. and somebody takes that book and loses that book. And now nobody can get access to that. And now everybody is basically paused. They just can't access that. So that's also another problem that, you know, when you want to use these critical sections, you need to get in and out really quickly. Same mentality of using an interrupt over here, right? You want to get in and out really quickly. So that basically just talks about what semaphores are. And semaphores are calling sleep and they're calling wake up. But this sleep and wake up is a direct operating system, system call. And so system call is basically saying that we are using the operating system's kernel API to access like the kernel's resources of, you know, the queues that the operating systems have in terms of the waiting queue, in terms of the ready queue, and then we can actually relegate this task into the waiting queue or the ready queue, right? So that's basically just saying that semaphores are not just regular sort of, you know, structures. They have access to, they have support of the operating system, right? So so there are many different types of problems, like the producer consumer problem, which is also known as a bounded buffer problem. So that's one problem. There's a readers writers problem. That's another problem. And so those are two kind of problems, and we can go through those two if you like. And then the other thing is that the processor can also have different ways in which it tries to solve this problem, right? Okay, questions?
Yeah, so first I was going to ask if we could, I guess, go through those examples you mentioned, but I'm still not understanding like the purpose of semaphores. Is it like to manage a queue of like processes that want to access like some critical piece of information to like manage a line to make sure people aren't all doing, you know, accessing like values at once? So I guess account balances at the same time.
Yeah. So you would use a semaphore over here because I want to make sure that nobody else gets to write and change any of the values related to the account balance when one of the tasks is reading and writing to the account balance.
But
So
isn't
here I would basically acquire a semaphore and then I would release a semaphore.
Oh, okay. I was going to say, but you still like there's still a critical section in acquiring and releasing, right?
The critical section is basically sandwiched between acquiring and releasing it.
No, but I mean acquiring and releasing itself is a critical section, isn't it? Because you can have like two threads like trying to access.
Yeah, so that's
at the
why
same time.
that's a good point, right? So you want to basically say, well, how can I make sure that, you know, when I get into this semaphore over here, when I do this down mutex, right? That I do not basically. So even after I've called down mutex, I can get preempted over here, or any time before this value is written to 0. So actually, even in this line over here, I could get. So you want to have some way to basically protect even calling the down mutex. Is that what you're saying? That when you
I'm asking, like, is there a way to like have completely foolproof code here where?
Okay. So that's a good question, right? So can you basically completely just lock down the code, right? So when I say that, you know, I want to lock down. So let's look at these. We'll basically go through the whole lecture, right? So
Okay.
So let's look at how, like, what are possible solutions, right? So you mentioned one good point that, sure, you want to use some kind of a semaphore, but when you call the semaphore, you could also get interrupted at that point. And sure, you can get interrupted, but once you call the semaphore, then you're not going to get interrupted. So the point is that once I execute the down semaphore, then I cannot get interrupted by anyone else, because I could get preempted as a task. They could run their task. As long as they are not running the same critical section code, that's fine. So one thing is that preemption is allowed, because that's like a higher level operating system, you know, task operation that says look, we want to maintain everybody's priorities. We want to maintain everyone's deadlines. And if you have a critical section, then that's something, that we will look into afterwards, right? So only if the other task is trying to execute the same code, then the critical section will kick in. If the other task is independent and doing something else, then the critical section problem is not going to kick in. So if you have captured a semaphore, you still can get preempted. But now if the other task that preempted you is trying to access the semaphore, access the critical section, then it is put to sleep. So here's an example, right? So say I have a low priority task that is running, and it has captured the critical section, and then it gets preempted by a high priority task. So now the high priority task is starting to run, and the high priority task says, hey, I'm the boss, I should be able to run whenever I want to run, and get off the road, you low priority task, right? But then as soon as it starts to execute, access the critical section, it says, oh, the low priority task has my critical section over here. And the low priority task says, haha, look, you got to go to sleep now, and I'm going to run. And only once I'm done running, then you can get back to running after this point. So what happened was we had a low priority task. It was operating first, and a high priority task came in and said, get off. I'm going to run at this point. But the low priority task said, hey, you're trying to access this critical section that I have already started accessing, so you need to get off. And then it kicks the high priority task into the waiting queue. And then once it finishes, and the high priority task comes in. So this is an example of where preemption is allowed, but access to the critical section is not. And in the next lecture, we will look at what is called, the synchronization problems with operating with task scheduling, where you basically cannot, a lower priority task prevents a higher priority task from running. So, but in this case, let's look at what can we do? Like what are good and bad solutions for accessing this critical section, right? So we could disable interrupts. As soon as before I start the critical section, I could say, look, global interrupts, everybody is gone. Global interrupts are not allowed anymore. But that's bad, right? Because that basically tells you that one task or one thread can just disable global interrupts whenever it wants. And that's it. You can't get any IMU updates. You can't get any sensor updates, nothing over there, right? So it's basically controlling the whole system now because that one task is running. So it's too big a hammer for, all you want to do is protect your critical section. You don't want to say nobody has access to anything else. So if you basically disable global interrupts, it also means that the kernel can't interrupt this task, and it can't run a higher priority task. So it's just saying all the power now is running with this current task because it's in the critical section. But that makes no sense, because all your task is trying to do is protect the critical section. It's not trying to protect the entire operating system, right? So so then what happens if if there are it stops any updates, or it stops any scheduling. What if the logic is bad in the critical section, then, and it has a sleep, or it takes too long to execute? What if the critical section has a dependency on some other interrupt? Suppose I get into the task, and then I have a critical section, and then I basically go into the critical section, but I say I'm waiting for a network packet. And so till it gets a network packet on the Ethernet port, it's not going to do anything. And it's just sitting there in this critical section. It has disabled all interrupts, and it's just waiting for this packet. If this packet doesn't come till tomorrow, the whole system is just frozen till that time, right? And that's a really bad solution to basically. So this is also so this whole lecture is full of interview questions, right? They would say, why is disabling interrupts bad? Give me 3 reasons. I've given you 5 reasons over here, right? So, so similarly, if you have the advantage obviously is that, disabling interrupts means that nobody can come in your way now. You are the boss, right? I mean, no matter how low priority your task is. And so this used to be used before in, in simple examples, but now when you have multi-threaded kernels, then you don't want to use that, right? So you could use something that is that then people started developing different approaches. They said, hey, how about we develop a new assembly instruction that can then support this? So this is like a test and set locks would be another one. Lockstep synchronization could be another one. So they said, okay, well, let's see, we can have while locked, then we go and lock it. So we basically are waiting while this process is locked over here. We're just waiting. Once it gets released, we go ahead and lock this, then we do our critical section, and then we unlock this, right? So this is, I think, the question that you had, where you want to sort of say, okay, well, there's a race condition in setting the lock over here, right? So that means I've just gotten into this, I finished this line of code, but I just get preempted at this point, and then another task runs, and then it gets into the critical section, and then I get to run after that, and I capture the lock. So basically there is this gap over here between this while locked and locked equals 1, where another task can come in, execute. And so this is still porous, because there is we can't basically solve this problem by just running like C code without any additional support from the hardware or the operating system. So does everybody get this? So this is the same issue as the bank example, the bank balance example, because even though it gets unlocked and I come and I've just finished that line of code, I can get interrupted right here, and that other task starts running, and then that other task could finish, or this task could basically get scheduled, because other task goes into the waiting or basically gets preempted back so that I can run, and then I lock this section. So basically implementing a solution in plain vanilla C is not going to allow you to have an atomic instruction over here. So a third one could be, say, okay, let's take turns. Okay, why don't we just be fair? Okay, so two of us are there, thread 0 and thread 1, and then thread 0 says, okay, right now, if it's not my turn yet, then just wait. And then I'm waiting, and then suddenly this turn basically gets updated while I'm just checking this, because another thread is running, and it says, okay, it's now the turn is thread 0's. If it's thread 0, then basically I go capture the critical section, and then I say, okay, well, turn 1, now it's your turn. So this is like a really friendly way of doing things, right? That I say, it's exactly what I said in the beginning of the lecture, that I have these two kids, and they just take turns with using the same toy, right? They always want the same toy, and then one kid says, okay, now can I take the toy for 2 minutes or 5 minutes? And then the other kid says, yeah, you can take it for 2 minutes. And then after 2 minutes, then the other kid asks, now can I take it for 2 minutes or 5 minutes? And then so it's fair, right? But why is this a bad idea? Who can tell me, like, who can give me an example of why this is a bad idea? You have the disadvantage there, but who can give me an example that it's a bad idea?
I feel like this still has the same original problem, where it's like, if thread 0 manipulates a value, like when thread 1, like thread 1, couldn't it have a different copy of that value before it gets manipulated? Or like, I don't necessarily see how that even solves the problem of like the example.
It solves that problem because now we are both sharing the same variable, right?
Oh, okay.
So in that case, I mean, even in the previous example, we are sharing the same variable of locked, but there it is locked, 1 or 0, and there you can grab the lock if lock is 1. I mean, so here, like, we are saying locked. Okay, basically locked equals 1 means it's locked, right? So if basically locked is 0, then you can set it to 1 and I can set it to 1. We both are trying to set it to the same thing. But in this case, you're saying, look, Rahul, now it's your turn. And then I say, no, now it's your turn. And then now it's your turn. And then we just take turns.
Yeah, but
So we are not setting it to, we're not setting turn to be 1. We are setting turn to be your turn is 0, my turn is 1. And then we are basically saying it's your turn or my turn.
okay.
So we solved, so we are making some progress, right? We solved that problem, that we are not both trying to set it to the same value. We have different values to set, and when the value is 1, then I have it. When the value is 0, you have it. So it solved that problem.
Correct.
Yeah. So what I'm looking for is what's an example of where it actually doesn't work too well. Yeah, go ahead.
Isn't it also doing constant system calls on each one to check the while loop, like wasting resources?
Making, one sec, what happened to it?
Like
I mean,
if
look,
it's
it is polling. It is polling, and because there is no preemptive operating system in this case, it's just saying I'm going to wait till it's my turn. But the thing is, the operating system could just it would just not run this thread when it's not running this thread, right? So then it just puts that thread to sleep. So it doesn't matter if it's still waiting. So yeah, so it is polling, but it's only polling when it is the running task. So yeah, it is not the most efficient piece of code, but the question is, what's an example of the disadvantage, right? The disadvantage is written down there, but what's an example of that? Like what's an example of a task that wants to run fast versus what's an example of a task that wants to run slow, or that runs slow? Yeah, exactly. So here we have self-driving car, and then it's basically waiting for the steering before it, to finish braking. It has to wait for steering to finish before braking if they both rely on the speed variable. So like in this case, in the self-drive, in the car example, say the braking is happening, very if one of the things is happening very infrequently, I'm only checking. I want to check the braking, say every 5 milliseconds, and I want to update the steering every 30 milliseconds, for example. So then now in this case, since it's the steering's turn, braking's got to wait for 30 milliseconds, and braking can't, it can't wait for that longer time, right? So that's the problem over here, that the slow job, suppose the slow job of, say the slow job of updating the steering is taking 30 milliseconds, then we just have to wait for that turn over there. So now because we are taking turns, right? So so you can, let me give you like a more intuitive example, right, of what's an example of taking turns. So say you want to like you're sharing like some video game with a friend, and you're just like, hey, I want to play this game, like every evening, but your friend is like, yeah, I can give it to you after a week, and then you basically lost like 7 evenings over there. But both of y'all can basically play the game at most once a week, so both of y'all are reduced to the speed of the slowest task over there, because you're like coupled now, right? So that's the problem when you commit to some long-term relationship, that now you're like coupled, and now you'll have to synchronize with each other on everything, right? So yeah, I'll give you another bad example. Say like you go to the toilet and you take a shower, and you're done with the toilet like in like 5 minutes, right? Let's say, and your roommate takes like 30 minutes. So you want to just make sure that as soon as your roommate wakes up, you just rush to the toilet, because you don't want to wait for 30 minutes, right? Because otherwise, if you just wait, then your roommate is going to take 30 minutes, and now you're locked into the longest waiting time, because that's what you have to wait for the other task, right? So thread 1 has to wait for thread 2 to finish, and thread 0 has to always wait for thread 1. And so that's a disadvantage, that we are basically taking two asynchronous tasks which should be allowed to run asynchronously, but we are synchronizing them. We're saying, no, now you run in a sequence, one after the other, one after the other, instead of being able to run independently. Right? So so we got rid of the first problem that we had before with these locks implemented in C, because we're not changing the variable to the same value. But then we got stuck that we are taking turns over here. So here's an example over here of like, using this lockstep synchronization. We have thread 0. It says, keep running this thread forever. While it is, not my turn, keep waiting. When it's my turn, get into the critical section, set the turn to the next thread, then do some other stuff outside of the critical section, right? So I come out of the critical section, then I set the turn to be this. And then thread 1 runs forever. It says, while it's not my turn, keep waiting. Once it's my turn, then get into the critical section. And once I'm out of the critical section, let the other thread use it. And so this solution works, but turns any asynchronous threads into synchronous threads. And that's not necessarily a good thing, because it's just going to slow down the system to run as slow as the slowest task over here, right? So now any questions regarding that? Was that not, if it's not super clear, ask. Okay, so we have about 20 minutes left. So what I want to do is spend the next 8 minutes or so and cover like how can we get some help from the processor, and then we'll spend about 10 minutes going through these 2 examples at the end. But the point is not to just do a standard lecture, ask questions, then we can address those along the way. So so let's look at the different ways in which we can have dedicated CPU instructions, right? So these are basically assembly instructions that we can use to manage concurrency problems. And so there's test and set, compare and swap, fetch and increment. And these are basically is like similar but slightly different approaches to manipulating this. And so what I'll show you in the next couple of slides are the C implementations of what this would look like. But actually it is implemented as a single atomic instruction. It's not implemented in C like this, right? I mean, it's not implemented as a C implementation. It is actually an assembly instruction called test and set. And what it is actually trying to do, I'm just showing you how you would implement it in C, but it is atomic because it's a single assembly instruction. It's just taking like a pointer to a lock value, and it is saying, okay, well, what's the last value over here? And it is setting that value to be 1, and then it is returning the last value, right? So it's just saying, okay, well, while test and set is equal to 1, just keep waiting over here, right? So it's just saying, okay, what is the last value? If the last value if it is locked by someone else, then the last value is 1. I set it to 1 and I return 1. So it's still 1. Okay, I read the value and I set it to 1 again and I returned 1. So it was locked in the beginning. I continued to let it be locked because I can't touch that lock. But if the last value was 0 and I set it to 1, then I return 0. Once it's 0, then I can go and do the critical section. And basically, once I'm done, I can just release the lock and say, okay, the lock is 0 now. I'm not using it. So when it's being used, the value is 1. When it is not being used, it's set to 0. So this test and set is actually a single assembly instruction that basically goes and checks what's the value of the lock. If the value of the lock is not 1, then it sets it to 0, and then it goes and sees that, right? So no, the question is, are these atomic instructions limited to CISC systems? No, these atomic instructions are also implemented in RISC-based systems, and you can find these instructions in RISC-based systems too. So test and set is actually like a really simple instruction. It's just looking at a particular value, running a compare, checking whether that value is equal to 0. And if it is 0, it's setting the value. And if it is 1, it's setting the value. And all it's doing is it's just returning that, right? So it's just reading a value, making an update, And so it is like it's basically like a add 1 plus to the same register, like that, right? To the same register value. It's very similar to that. The only thing is it's returning the previous value. So so in this case, so let's see, like so that's one example, right, of where the assembly instructions can allow you to do a test and set. And then but what is sort of what is the, like, even though we are using test and set over here, what's the disadvantage of using this? So think about that, right? So because I'll show you the disadvantage is kind of universal over here. So another example is compare and swap, right? So here we compare the value of a memory location with an old value. If they match, then we replace it with the new value. So let's break this down, right? So again, this compare and swap, C and S is basically CAS is basically also a single assembly instruction. I'm just showing you this what it would be like if we implement it in C code. It's not implemented in C code in reality. It's just implemented in hardware as a single assembly instruction. So that is what is missing from being written explicitly in these slides, but that's the commentary that you need, right? So compare and swap is basically taking the lock over here, the pointer to the lock. It has an old value, it has a new value, and it's basically saying, let me save whatever the value in that lock. If it is equal to the old value, then set the value to the new value and save, right? So if you were to grab a critical section, we set the lock to 1 only if the lock was still set to 0. Okay, so basically let's see how we use it now. So we do compare and swap while this, and we have our lock over here, and we want to set the old value to 0 and to 1. So basically we are saying that if the old value, if basically this lock was 0, then I can set this lock to 1, and then I'm basically locking it, and then I can run my critical section. Then I set the lock to 0. So it's kind of the same, but it's not exactly the same, right? So because here I'm explicitly giving it these values but in test and set, it's implicitly saying, was this set before? If it wasn't set, then set it and return the old value. But then I have to do that comparison. So here it's just returning the old value. So whatever I have, it's just returning that old value. And so it's again just checking, was the lock set before? If the lock was not set, then set it. If the lock was set, then set it. But just return the old value. If the old value is not equal to 0, then that basically means if the old value is not equal to 0, then I set it to 1. That means I locked it, and then I can get into this critical section over here. And otherwise I know that it was previously locked, and I just got to wait for that to, that if it was 1, if it was previously locked, then I just got to keep waiting in this till I can unlock it.
So when the programmer tries to access like a variable, so I guess the solution here is that you design a new ISA that includes this like assembly instruction for like a lock, and then whenever the programmer, they compile their code, and whenever their code tries to access a global variable, the compiler will automatically throw this instruction in.
Yeah, actually the programmer can just say, this is like in your C, you can actually interleave direct assembly code. So you can actually you can just say, look, the next set of lines of code till I say stop are all assembly code. So you can actually have C and assembly sandwiched between that. We haven't gone through that in coding. I mean, when I did my embedded systems, a sophomore junior course like this, we actually had to do that. We had to implement that code, but that would be a little too hardcore right now for doing that. But yeah, you're right. So either we call this function in C, and we say, hey, compiler, put this sort of compare and swap over here, or we actually just call the assembly code. It's kind of like you're already doing this, right? When you call SEI and CLI, what does SCI and CLI do? They just go and call that assembly instruction over there, right? But what's the difference over here is that you want to directly call this assembly instruction at this point. You don't want to make a C call to an assembly instruction. You want to directly have the assembly instruction here because you don't want any time, any chance of having porous non-atomic cores, right? So the whole point is that this call over here of compare and swap in this while statement is actually an atomic execution, right? Compare and swap not equal to 0 is an atomic execution over there. And that's really important. If it wasn't an atomic execution, then you would have the while loop would be porous too. And that's something we got to protect against, right? So if you go back to like now, we'll come back to, we'll do the last example of fetch and increment, and then I will ask you the same question. So great, the compiler is supporting this, the processor has these instructions. What's the problem then, right? Why are we still complaining? Problem solved. So let's look at this, right? Fetch and increment. This is like you're waiting in a queue. This is like the queue outside Trader Joe's. They say, well, or it's not necessarily outside Trader Joe's today. They just have a long line that goes, almost like quarter of a mile outside Trader Joe's sometimes. The model of the story is don't go to Trader Joe's or Whole Foods or any of these fancy places because too many people in Philly are going to them right now, or in any city, right? So it's just because that's what they're used to. So, but say you go to a driver's license place, right? And you want to get your driver's license. They say, okay, well, take a ticket. And then when your number comes up, like, say your number is 21 and it's right now 19, and you got to wait for 19 to finish and 20 to finish. When 21 comes up, then they show 21 on the screen, and then you go over there because you see that's your ticket number, right? So this is the same method of like, take a ticket. So increment a memory location, return its previous value, right? So let's see this fetch and increment. Again, this is also an assembly instruction, which is atomic, but I'm just showing you how it would be implemented if it was implemented in C and not in hardware. So it's saying fetch and increment, and we have a pointer to X. So we have we just basically take the last value, we increment the value, and we return the last value. And you're like, hey, wait a minute, that doesn't sound that smart. But let's see how we would use it, right? So say the ticket is 0 and the turn is 0 initially, right? So the ticket is basically saying, what is the current, value that is being served? Like now serving 90, the turn is basically the current now serving value, say it's 92, and you take a ticket, it shouldn't be A84, it should be something more than 92, right? Say it's 95. So I basically call fetch and increment, and I say, here's the ticket, whatever the ticket, like the value is 92 right now, and what's my turn, right? So now the current value that it is being served is 92. So then my turn will be after that, right? So, but you're like, wait a minute, other people could have called fetch and increment and they're also waiting for that, right? So let's look at what fetch and increment is doing. It's taking the last value and then it is just incrementing that value and returning that value. So it's basically taking, if the ticket is right now at 92, then it is just returning 93. And then I'm just going to wait till the turn is 93. Suppose someone came before me and the turn value was 91. Then they get 92 and they are also running this in their thread and waiting that when the turn is 91, then they get to run. But the turn could actually be 5 at this point, and then 6, 7, 8, 91, 92, then that thread starts to run. When it's 93, then I get to start to run. And then once I'm done with my critical section, I say, okay, I'm done with my turn. And then it basically just returns that turn over there, right? So, and here we're basically saying what is the turn number, and then the turn basically is updated to 93 after that point. And then say then 94, and then the next task can run after that point. So do you understand this? So there is the ticket and there's the turn. Okay, and we are basically incrementing these two things over here. Confused a little, not clear. So all it's doing over here is that it's just saying that, well, when I'm just getting a tick, my turn initially, and then that number can keep increasing as more and more people come and or more and more threads come and ask for, for the ticket, and the ticket keeps incrementing. And I'm checking what my turn is. And once my turn is done, I just say, look, my turn was 92, 93, I'm done. So now you can basically set that ticket value to something after that, right? So I don't care what the new value is, but I'm just telling you that I'm done. So it's just returning that once the critical section is done. So who can tell me why this? I'm not clear, right? So just refresh my memory. Why is this fetch and increment being called at the end of this critical section? We're calling it before and then waiting. And then we're doing this critical section. And then after the critical section, we're calling fetch and increment again. Could be a quiz question.
The way I understand it here, we're just at the end saying, okay, I'm done with the critical section, so you can increment the turn. So the next person with the next higher ticket then can access the critical section. Is that correct?
Yeah. So then we are basically saying that that turn is done, and so now we are just globally updating that turn over there, right? So because we are never actually saying turn equals turn plus 1. We are allowing that atomic function to actually do that, turn equals turn plus 1 over there. So that's important that we atomically increment it. But here the interesting part is, it's almost like decoupled. We're just getting a turn and waiting for our turn, and that could happen whenever. But it allows many jobs to basically wait in a queue, right? In a first come, first served queue like that. Okay, so any questions so far with this? So what are we like, what is essentially happening over here is that if you want to come up with a solution, right? So for managing these critical sections, we have to have certain conditions, right? And this you will learn even in other classes as you go to higher level classes. First, it means that no two threads can be in the same critical section simultaneously. You're like, yeah, obviously that's our whole goal, but we need to explicitly say this, right? That there's mutual exclusion. If you are in the restroom and it's a single person restroom, then nobody else can go into that restroom at that same time, right? So that's mutual exclusion. It's kind of like, accepted, right? Your roommate is not necessarily going to barge in every time and say, hey, I got to take a dump now, right? So then, because that's a mutual exclusion sort of, socially accepted thing, right? Generally. Progress, right? So if no, so this is also important. These are the rules that if any of these rules don't hold, then you don't have a solution. If no thread is executing in its critical section, but one or more threads wants to enter, the selection of the thread cannot be delayed indefinitely. That means it just says that if no one is using the critical section and you want to use it, then you can use it. We're not going to stop you we're not going to make you wait unnecessarily, right? We're not going to try to queue you up and then decide how to service the queue. The second is that there's bounded waiting. No thread should wait forever to enter critical section. So yeah, the critical section is busy now, but it will eventually get not busy or it will eventually get available. And we need to make sure that how long it takes to get available is bounded. We need to know what is the longest waiting time, right? So you wake up, you got to go for your physics quiz in the later in the afternoon, and then you tell your roommate, hey, how long are you going to take? He's like, oh, not more than 5 minutes. And you're like, okay, not more than 5 minutes, because that's bounded waiting. You need to go and get a shower before you go for the quiz, and 5 minutes is all you have, right? So no thread running outside the critical section, may block others. That's fine. And then a good solution will make no assumptions on the number of processors, the number of threads, or the relative speed of each thread. So we don't have this, dependency between the threads, like that, right? So then that leaves us, we're a little bit over time, but I'll just go through these two examples, and then if that's okay with you guys. Okay. You don't have to rush for another class yet. The walking time to DRL is 0 now. So, okay, so let's go to producer consumer example, and then we'll talk about this readers writers. It'll take us 10 minutes. Okay, so then after that, how about we just let me just pause for a second. I'll get some water, then we can continue. Okay, so the producer consumer example. So this is like a template of a problem that you find it's running in pretty much every distributed system has a version of this problem or the next problem. Your operating system is solving this problem. You run stuff on AWS, you run stuff on any kind of server. They're all having this problem. They all need to solve this problem for the system, and how efficiently they solve this problem is how much better throughput they have, how much lower latency they have, and accordingly so every time you make a Google request, dozens and hundreds of these problems have to be solved, and they have to basically resolve this really efficiently, because Google is getting like 1 billion requests at any point in time, and they need to resolve how do they only have, they don't have 1 billion processors. Let's say they have 1 million processors, right? And they have 1 billion requests. So how do they service these 1 billion requests and ensure that all these 1 billion requests have a bounded waiting time of no more than, say, 10 milliseconds? Because as soon as you start typing stuff, that response is there. It makes you wait for more than 50 milliseconds or more than 100 milliseconds. You basically can't tolerate that anymore. That's how spoiled we've become. But that's also part of their business model, right? That responsiveness has to be there. So the producer in this example, it generates items that go into a buffer. So think of it as we are having a networking, a TCP IP network, and I'm sending you packets. So I'm the producer, and I'm putting packets, I'm sending it over the link over here, and I'm putting it into your buffer that is in your local Ethernet card over there. And then I'm generating items and putting that in your buffer. And the maximum buffer space, say you say, oh, okay, I only have 12 packets worth of a buffer that I can have. And if basically I fill up that buffer, you say, look, producer, you need to stop sending me stuff till I can service that stuff. The consumer, that's you, you're picking up things from the buffer and saying, okay, what does he have to teach us this time? Okay, and then you're reading that, and then you're like, okay, well, if there's nothing in the buffer, you basically go to sleep, right? Aren't you guys sleeping way much better than when you were on campus? Okay, some of you are gaming a lot, but that's a good life. Okay, exactly. So so either you're sleeping a lot or gaming a lot, but both are good things, right? So this is the bounded buffer problem. Let's take a look at this, right? So we have a producer that is producing items and putting them into this buffer. So so how do we run this? Now the producer, so what is the main issue here is that the buffer is shared between the producer and the consumer, right? If the buffer is empty, the consumer can't consume anything. If the producer is trying to put something in the buffer, and then the producer and the consumer removes something at the same time, then all the accounting would get mixed up. It's kind of like that linked list problem earlier in the slides, which you should definitely go and revisit. So it produces an item, it has produced something, right? So that's, and then it has to basically say, okay, well, decrement the empty count in the buffer first. So the buffer has 12 units that are empty, decremented to 11 units that are empty. And then it basically then has another mutex over here. It adds the item when it's accessing the buffer. And then it basically ups the mutex once it's stopped accessing the buffer, finished accessing the buffer. And then it basically does up for basically incrementing the full list. So what do we have here now? We have a mutex, we have empty, that's the initialized to say the number of buffer units that we have. And the full is 0 because initially we don't have any units. So, and then now the consumer on this other side has down buffer and says, okay, well, I'm going to consume one item. So whatever the full count is, I'm going to decrement that. Suppose it had 8 items. I'm going to take one item from that and I'm going to make it 7. And then I'm going to actually go and physically remove that item from the list. So I'm going to access this buffer. So I need to have a mutex for that. And I basically get the item. And then I basically go and update the empty count. And I say there's actually one more empty slot now. And then I go and I consume that item. When I consume the item, I can do that outside of the outside of the critical region, right over here. It's just that when I'm putting something in the critical section or when I'm taking something out of the critical section, then I need to have that mutex over there. So now my question to you guys is, why don't I just have this mutex and be done with it? Why do I need to have another mutex with empty and another mutex with full? This is like a Facebook, Google, Apple interview question. In fact, it's too vanilla for them to ask you this, but for sophomores, they will definitely ask you this. So why do I need empty and full? Why, I could have just been fine. So far, we just worked with mutexes and we just had one mutex for the critical section. But why do I need like a down empty and an up full like that? Give it a shot.
Does it let someone else know which user is trying to access the information?
Nobody knows which user is actually accessing anything because we are just communicating through these variables, right? There is no identity communicated.
Well, I noticed that because they're in the opposite order.
Yeah, that's a good point. You notice that when I'm producing stuff, I'm basically saying that it's less empty and it's one more. So that's a good observation. That's actually a good hint to you're on the right track. You just have to think a little bit more. Yeah, don't think somebody else will answer it. Why someone, I'm saying that to everyone. You answer it, right? Everyone's like, yeah, I'm sure someone else will come with the answer. I'll just look cute here. All of y'all look cute. It's fine. Now let's answer the question.
My guess would be that there are 3 different operating modes, basically both consuming, or basically the producer's producing and the consumer's consuming. Then one operation mode is when the buffer is full. The producer is not allowed to produce anymore and has to wait until the consumer has consumed enough, and then vice versa.
Yeah, exactly. So this is the right intuition. So the producer can, as it's producing, if it cannot enter the buffer if the buffer is no longer empty, if there's no empty unit. So then it has to just stop. It's saying stop, the buffer is full. So it could not get past that down empty, the first down empty right there. So the producer has produced an item, but it just can't touch the buffer. So it's blocking that, right? So we want to make sure the buffer is never over full or under empty. if that makes sense in English, right? So it's never more empty than zero, right? If that also makes sense. So that's the problem over here, right? So similarly, now let's just start with the beginning. The consumer shouldn't consume anything if the buffer is actually there are no items there, then it just has to wait. So that's basically just the entry problem. I'll just call it the entry problem, right? And then the rest of it is the opposite, right? That when you have added an item, you basically update full. When you've removed an item, you just update empty. So this is just saying that how can we need to have another mutex to block the producer from overproduction, and we need to block the consumer from overconsumption, like that, right? So that's why we need 3 mutexes. So how do you think of, when I studied this as a sophomore, man, it was really difficult to understand these things, and I was like, how did they come up with 3 mutexes? And so then my professor, who then became my PhD advisor after that, he was like, just think about it. What are the rules that you have? Let's go back to the problem, right? The problem statement basically says, we want to share this buffer. Great. That means we need a mutex. Okay. So only one process. Sorry, So what are the rules here? So the producer, if the producer, there's a producer rule, if the producer fills the buffer, it must wait. If the consumer basically has nothing to consume, then it must wait, right? And we had a shared mutex. So we have 3 rules. For 3 rules, we have 3 mutexes over here. That's it. It's just that simple. It's never that simple, but basically you just need to count what are the rules. And then what's tricky is figuring out this order. Okay, there's empty here, there's a mutex. The mutex to me, which box over here is there, that's the easiest part. But to me, what was confusing was, figuring out, oh, full comes first and then empty comes. In this case, empty comes first and then full. So to me, that's the confusing part. So I'm just like kind of pinpointing to you why you would get confused in this type of problem in the future. So the second type of problem, which will end in 5 minutes, then is basically a variation of this problem. So it's a multiple readers writer problem, right? So if you have a file, allow only one process to write at a time. So that's the rule. But multiple readers can read at the same time. So only a single writer can be allowed to write at a time. Multiple readers can read at the same time, but no readers can read while the writer is writing. Okay. So where are you using this? Where is this problem being solved at least 10,000 times a day for you? How many of you all use Google Docs? Yeah, this is why we left the old school Word, and we left Dropbox and Box, and we just switched to Google Docs, right? Because Google Docs is like, you can write line 1, I can write line 2. And actually that's how we make, that's how we were preparing yesterday's lecture for the autonomous racing. The whole team was making like different slides at the same time. And we did the whole presentation in parallel in 1 hour. And then we could teach the class after that. So here we have some rules, right? So think about what rules we have here, right? So let's look at how this readers writers. So this is just saying that we have some kind of asymmetry, that only one writer at a time. If the writer is writing, then no readers. I can have multiple readers at the same time, and that's fine. So I have a mutex that's basically saying, can only be used. Critical section can only be used only by the reader. Can write, that means critical section for n readers versus 1 writer. Let's see what that means. And then we have the number of readers that are there, right? So the writer over here basically says down. So it's writing forever, but whenever it wants to write data, so it says can write and block if we cannot write, and then writes the data and then says, okay, anyone else can write. The reader is a little bit more complex here, right? So the reader basically says down mutex over here, and then it says, okay, plus count for the reading count. If I'm the first reader, then I can say, I do down can write. Basically it's saying that I'm the first reader and I don't allow any writer to come in at this point because we are reading at this point. And then it basically ups the mutex. It's done with updating the variables. Then you can do the read after that. So when we are doing the read, there's actually no mutex actually active over there because we've blocked any writer from coming in. But if we are not and then when we are done with reading, then I can say, okay, down mutex for the reading. Sorry, I made a mistake. When I'm reading, I just have this simple mutex over here, right? I'm up mutex, do the read, then down mutex, and then I do the read count. Basically, I finished reading. I want to go away now, and I'm done reading that. And if the read count is 0, if I am the last reader, then I say, okay, up can write, and then I do up mutex, and I'm done. So this whole thing now is a big critical section. I mean, this is the main critical section that I have here. But to enter this, I have a gate that says if you are the first reader, then you need to update this can write. If you are the last reader, then you need to update this can write over here. Because the first reader prevents any writer from coming in. The last reader says that now a writer can come in. But if you are like reader number 2 or 3, then it just basically you just go and do the read, and that's fine. You can keep upping the mutex. And you can just keep a read count, right? You can say, okay, maximum readers are 12, for example. And then once it becomes 13 readers, and that reader does not come in and gets blocked over here. But so you can actually have multiple readers, but only a single writer. So does that make sense? Somewhat kind of confused. Okay, it looks fine, right? So if you want me to go through this again, I can go through. I'll just go through it once again. So basically with the writer, let's go back. We'll do this in 2 minutes. So the writer can just checks, okay, can I write? If it says no, you cannot write because there is 1 or more readers, then it basically is blocked and is waiting over there, right? So and then once it gets cleared and the last reader leaves, then it says yes, you can write, go and write. Then it starts writing, and it has captured the mutex over here. Once it's done writing, it basically says, okay, well, anyone else can write, or for that matter, can read. So, but in the reader, we only care about the first reader and the last reader as special cases. And so the first, we just do the read count plus. So, and in this case, we allow as many readers to come in. And then if we are the first reader, then we say, are you read count equal to 1? Yes. Then we basically say, okay, well, now we need to prevent the writer, disallow the writer from writing. Then you go ahead, have a mutex, and do your read after this point. You up your and then now, and once you're done with your read, we basically get out of that mutex, and then we do the read count minus, and then we just set the read count over here. It says, okay, if the read count is, if you're the last reader, then basically allow writers to write, and no more readers are left. And then you up the mutex over here, and then you're basically done after that point, right? So every time you enter a critical section, you down the mutex, get out of the critical section, you up the mutex, you do your reading, which is out of the mutex now. And then, because if you have a mutex while you're reading, then other readers can't read, right? So that's important over here. It's kind of the opposite. The reading activity is not within a mutex, actually. Right. So, and then once you're done with the reading, then you again want to update your variables, but you want to do that in an atomic section over there. So any questions with this so far? I think if you understand, basically there are 3 stages to understanding this. One is understanding the types of problems you have with race conditions. That's like the bank problem, and that's like updating the linked list. Then you look at, different ways you would try to solve the problem. Why are these different ways broken? Like, using interrupts. And then, then we look at we look at the hardware-based approaches that you can use. And so one thing I forgot to mention in the hardware-based approaches, there's always a busy loop or a spin lock. That's always a while waiting for the hardware, based instruction to say it's my turn. So I'm always waiting there, right? So, and that was pointed out that that's a little bit wasteful. It's kind of a polling sort of thing over there, right? And with the mutexes, there's no polling. Why is there no polling with the mutex? You see, I don't have a while one over here. I just have if statements.
Is it because the operating system then puts that task to sleep?
Yeah, the whole point is that it's a very energy efficient and resource efficient way doing this. You don't have to keep waiting for whenever that your chance is there, right? The operating system says, hey, why don't you just take a nap? Why don't you go play, what about some Fortnite or something like that? Then come back, right? So that's the benefit of having these mutexes over here. Now, yeah, it is a little bit magical that the operating system is managing that, but we covered that at least abstractly, right? How the operating system runs the queues. And we're trying to figure out how to have your lab run on a simulator in Detkin lab for the next lab. But now that you have this super extension for the current lab, ask questions. So I think you guys are, let's see how many people are on here. You guys are the few, well, it's just 6 of you all, right? I think it's usually the same, or it's like 8 people over here. It's usually the same kind of, or 6 people in this. So the rest of the class is not on this, right? On this. So, and that's why they ask this same question that we covered in the lectures here. But that's their problem, right? So you don't even have partners now. So for the lab, you should just get started. It will take like 20 hours to do this current lab, and so the extension, make use of it. The problem with the extension is that everything coincides on the same day. You have a worksheet due on the same day, you have the lab due on the same day, and you have a quiz on the same day, right? That's why we always stagger the quizzes to not be due, but since we moved this lab to our off week or the quiz week, so you have everything due on that same day. But I think you'll be fine for the quiz if you understand this lecture well enough then, and the OS stuff well enough. Okay, any last questions? It's already 1:43, so we can stop here otherwise.
Yeah, I have a question. So
Okay.
Is there another quiz this week, or?
Not this week, next week.
This lab, the Gamulator lab, is due this week, right?
We gave you an extension to next week. I'll send out another post. It was nested in one of the posts. So.
Oh, okay.
Yeah. So the Gamulator lab is not due this Friday. It's due the following Friday.
This recording will be posted either on Canvas or Piazza, right?
That's right. I post everything is on the same. It's the same link.
Okay. Thank you.
Okay. So there was a question. Okay, this was long ago. Okay, I didn't see this question. Do you all still have this question? I guess not here anymore. Okay, any other questions you guys have? All good? Okay, give me a thumbs up.
For the Gamulator, I still have one question.
Yeah.
So the tasks got extended, so it's not just that original PDF that you sent us that we have to solve.
It's the same. It's just the same lab. It's just the deadline got moved by a week.
Oh, okay.
Because many people asked for it, and normally we wouldn't give a thing, but now we have to be soft. So.
Okay.
Or nice, or whatever you want to call it. Yeah, we are very nice. The problem is that it's going to cascade to, you have the quiz and the worksheet, so we'll have it all. But ask questions. All the TAs are working super hard. So you don't see that, but they are, because we are really trying to figure out how to put your next labs online. Yeah. Okay, guys. Any last questions, or you can ask? Okay, all good. Okay, all right. Have a nice Tuesday, and I'll see you guys on Thursday. Bye.